The hottest thing you've ever experienced isn't even close. Not fire, not lava, not the surface of the sun. Right now, in the most powerful machines humans have ever built, inside the CERN, scientists briefly created temperatures over 1 trillion degrees, hotter than the center of a supernova, hotter than the early universe microseconds after it began. And yet, even that is nowhere near the true limit. Because physics doesn't just ask how hot things can get, it asks something far stranger. What happens if temperature doesn't stop increasing? What happens at infinite heat? At first, it sounds meaningless. Infinite temperature feels like a broken idea, like dividing by zero. But in physics, it's not nonsense. It's a doorway into the behavior of matter, energy, and even the structure of reality itself. To understand it, you have to let go of what heat feels like, because heat is not fire, it is motion. Every object around you is made of atoms, and those atoms are never still. Even in a solid, they vibrate. In a liquid, they slide past each other. In a gas, they move freely, colliding, bouncing, constantly changing direction. Temperature is simply a measure of how much these particles are moving. The faster they move, the hotter the object. If you cool something down, motion slows. Push it far enough, and you approach absolute stillness, the point known as absolute zero, where motion is minimized as much as the laws of quantum mechanics allow. But heating is the opposite journey. You're not adding heat as a substance, you're injecting energy, forcing particles to move faster, collide harder, vibrate more violently. At everyday temperatures, this is gentle. Molecules drift, bump, rearrange. At higher temperatures, things begin to break. Molecules can't hold together anymore. Bonds snap. Electrons start to separate from atoms. Matter changes phase, not just from solid to liquid to gas, but into something far more extreme, a plasma. In plasma, atoms are no longer intact. Electrons are ripped away, leaving behind a chaotic sea of charged particles. This is the state of matter inside stars, including the sun. But even plasma isn't the end, because temperature can keep rising. As energy increases further, even the structure of atomic nuclei begins to fail. Protons and neutrons, once tightly bound, start to lose their identity. At temperatures above trillions of degrees, something remarkable happens. Matter dissolves into its most fundamental components. Quarks and gluons, normally locked inside protons and neutrons, become free. This creates a state known as quark-gluon plasma, a substance so extreme that it hasn't naturally existed since the first moments after the Big Bang. In those earliest fractions of a second, the entire universe was this hot, not made of atoms, not even made of particles as we know them, just a dense, chaotic fluid of fundamental energy. And when scientists recreate these conditions in particle collisions, they're not just making something hot. They're briefly turning matter back into its primordial form. But even this unimaginable state, is still not infinite. It's just another step. Because as temperature rises further, something deeper begins to break. Not just matter, but the very framework we use to describe it. At extremely high temperatures, something subtle begins to shift in how energy behaves. Up to this point, you can think of heating as simply adding more motion. Particles move faster, collisions become more violent, structures break apart. But underneath all of this is a statistical rule, a quiet law that governs how energy is shared. In any system, energy doesn't just pile into one particle, it spreads out. Some particles move fast, some slower, most sit somewhere in between. This distribution is not random, it follows precise mathematical patterns described by statistical mechanics. As temperature increases, this distribution stretches, more particles occupy higher and higher energy states. But here's where things become strange. To truly reach infinite temperature, you don't just need particles moving extremely fast, you need something far more extreme. Every possible energy state must be equally populated. Low energy, high energy, it no longer matters. The system loses preference. There is no typical motion anymore, no equilibrium in the usual sense. Everything becomes maximally disordered. This is not just hot. This is complete randomness. In normal conditions, systems tend toward order in a very specific way by maximizing entropy. Entropy is often described as disorder, but more precisely, it is the number of ways a system can arrange itself. At higher temperatures, entropy increases because there are more accessible states. But infinite temperature represents a limit. It is the point where entropy is maximized completely, where every configuration is equally likely. There is no structure left to break, no pattern left to disrupt. If you try to push beyond this, physics doesn't behave the way you expect. The idea of hotter begins to lose meaning. Because temperature, at its core, is not just energy, it is defined through how entropy changes with energy. And at this extreme boundary, that relationship starts to collapse. To see why, consider how temperature is formally defined in physics. It is not simply how much energy something has. Instead, temperature is tied to how adding energy changes the entropy of a system. In precise terms, temperature is related to the inverse of how entropy changes with energy. 1 over T equals partial S over partial E. This equation quietly reveals something profound. If adding energy increases entropy, temperature is positive. This is the world you are familiar with. But if you reach a point where adding energy no longer increases entropy, or worse, starts decreasing it, the definition itself breaks intuition. Mathematically, this allows for something unexpected, not just infinite temperature, but temperatures beyond infinity. To understand what lies beyond infinite temperature, you have to accept something that feels impossible at first. Temperature can become negative. Not cold, not below zero in the everyday sense, but genuinely negative. This doesn't mean a system has less energy than absolute zero. That would violate the very foundation of thermodynamics. Instead, it means the relationship between energy and entropy has flipped. In most systems, when you add energy, disorder increases. There are more ways to arrange the system, more accessible states, more randomness. But imagine a system with an upper limit to how much energy it can hold, a ceiling. In such a system, as you keep adding energy, you eventually start running out of available states. Instead of increasing disorder, you begin forcing the system into more specific, constrained configurations. Entropy starts to decrease. And when that happens, the definition of temperature, the one tied to how entropy changes with energy, crosses a boundary. It doesn't pass smoothly through infinity. It flips from positive to negative. Here's the part that sounds completely wrong, but is absolutely true in physics. A system at negative temperature is hotter than any system at positive temperature. Hotter than boiling water, hotter than stars, hotter than the quark gluon plasma created in high-energy collisions, even hotter than infinite temperature. Because heat doesn't flow from higher numbers to lower numbers. It flows from systems that are more likely to give up energy to those that are less likely. And negative temperature systems are unstable in a very specific way. They want to release energy immediately. If you place a negative temperature system next to any positive temperature system, energy will rush out of the negative system into the positive one, from negative to positive. Which means, in a very real sense, negative temperature sits beyond infinity on the thermal scale. This isn't just theory. Physicists have actually created negative temperature systems in the lab. Not with everyday matter, but with carefully controlled quantum systems, like spins in a magnetic field or ultra-cold atoms trapped in optical lattices. In these systems, energy levels are limited. There is a lowest state and a highest state. By manipulating them precisely, scientists can force particles into higher energy states in a way that reduces entropy instead of increasing it. The result is a population inversion, more particles in high energy states than in low energy ones. This is the defining signature of negative temperature. And it's not just an abstract curiosity. It's closely related to how lasers work, where energy is stored in an inverted distribution before being released as a coherent burst of light. So negative temperature is not just real, It's something we already use. Now step back and look at the full picture. At low energies, systems are ordered. As you add energy, disorder increases, temperature rises. Push further and you approach a limit where all states are equally filled. That's infinite temperature. Beyond that, adding energy forces the system into decreasing entropy. Order, in a strange sense, begins to re-emerge, not as structure, but as constraint. And temperature becomes negative. This creates a thermal landscape that doesn't run from cold to hot in a straight line. It bends, from absolute zero, through familiar temperatures, up to infinity, and then continues into a regime that behaves in the opposite way. So far, heat has been about energy inside matter. Faster motion, broken bonds, free quarks. Even the strange regime of negative temperature still depends on systems with well-defined energy states. But what if you keep increasing energy density, not just in a system, but in a region of space itself? At some point, energy stops behaving like something inside spacetime. It starts shaping spacetime. According to general relativity, energy and mass are not separate from gravity. They are its source. The more energy you pack into a region, the more spacetime curves. At ordinary scales, this curvature is negligible. At extreme scales, it becomes dominant. And at a critical threshold, something irreversible happens. If enough energy is concentrated into a small enough volume, spacetime collapses into a black hole. Not because of matter alone, but because energy itself gravitates. This means that an attempt to create arbitrarily high temperatures in a confined region doesn't just make things hotter, it risks triggering gravitational collapse. Instead of reaching infinite heat, the system forms an event horizon. Energy becomes trapped. Information cannot escape. In a sense, gravity intervenes before temperature can diverge. But black holes introduce an even deeper twist. They are not cold, dead objects. They have temperature. Through quantum effects near the event horizon, described by Hawking radiation, black holes emit radiation as if they possess a temperature inversely proportional to their mass. Smaller black holes are hotter. Larger ones are colder. This creates a paradoxical situation. The more energy you compress into a black hole, making it larger, the lower its temperature becomes. So instead of reaching infinite heat, adding more energy can actually reduce temperature. The relationship between energy and temperature has completely inverted again, but for a different reason than before. Now imagine pushing this to an extreme. If you tried to create a region of arbitrarily high energy density, two competing effects would emerge. One pushes temperature upward, more energy, more excitation, more extreme states of matter. The other pulls temperature downward, gravity locking that energy behind horizons, diluting its observable effects. This tension suggests something profound. Infinite temperature may not be physically achievable, not because it's undefined, but because the universe has built-in mechanisms that prevent it from being realized in any observable way. Either matter breaks down into fundamental fields, or space-time itself collapses. And this leads to one of the deepest frontiers in modern physics. At sufficiently high energies, far beyond anything we can currently test, the known laws of physics begin to conflict. Quantum mechanics describes particles and fields. General relativity describes space-time and gravity. At extreme temperatures and energy densities, both must apply simultaneously. But they don't fit together cleanly. This is the domain where a theory of quantum gravity is required, a framework that can describe what happens when space-time itself becomes subject to quantum uncertainty. Some candidates, like string theory, suggest that at these scales, particles are no longer point-like, but extended objects. Others propose that space-time itself is not continuous, but made of discrete units. If that's true, then infinite heat might not just be unreachable, it might be meaningless, because below a certain scale, the very concepts of temperature, space, and time could lose their definition. In the earliest moments after the Big Bang, the universe was not just hot, it was in a state where temperature, energy, and space-time were inseparable. Within the first tiny fraction of a second, temperatures were so extreme that none of the structures we rely on, atoms, nuclei, even protons and neutrons, could exist. Everything was a dense, rapidly expanding field of energy. As we trace this backward in time, temperature rises sharply. Denser, hotter, more uniform. And if you follow the equations of standard cosmology all the way back, they lead to a singular point, a state of infinite density and infinite temperature, a singularity. But this is where physics sends a warning. Not that infinity exists, but that the theory has reached its limit. A singularity is not a physical object you can observe or measure. It is a signal that the equations we're using, based on general relativity, are no longer sufficient. They predict infinity because they're being pushed beyond their domain. At scales this extreme, quantum effects cannot be ignored. Space-time itself is no longer smooth. It fluctuates, distorts, possibly even fragments. Instead of a clean, continuous fabric, reality may have been more like a turbulent, uncertain foam. In this regime, the very concept of temperature becomes unstable. Because temperature assumes a system in statistical equilibrium, particles, energy states, distributions. But near the beginning, there may not have been well-defined particles at all. Only fields, only fluctuations, only probability. There's a theoretical scale that marks this boundary. It is known as the Planck temperature. This is not just very hot, it is the highest temperature at which our current physical theories can meaningfully describe reality. Beyond this, our equations lose predictive power. At this scale, gravity becomes as strong as other fundamental forces. Quantum effects dominate space-time itself. Distances and durations approach their smallest meaningful units. Trying to go beyond this is like asking what lies north of the North Pole. The question itself may not make sense. So does infinite heat exist? Mathematically, yes. Physically, everything we know suggests a different story. As systems heat up, they don't smoothly approach infinity. They transform. Matter dissolves into particles. Particles dissolve into fields. Fields begin to interact with space-time. Space-time curves, collapses, fluctuates, and at each stage, the meaning of temperature shifts, until eventually the concept itself may no longer apply. This leads to a subtle but powerful realization. Infinite heat is not a destination the universe reaches. It is a boundary, a signpost marking the edge of our understanding. Every path toward it is interrupted by quantum limits, by gravitational collapse, by the breakdown of space-time, or by the loss of meaningful definitions. The closer you try to get, the more reality changes its rules. Now we enter one of the most subtle limits in physics, where heat is no longer just a property of matter, but becomes tied to information itself. When you keep adding energy to a system, something important happens that is easy to miss at first. The number of possible microscopic configurations increases. Every particle can move in different ways. Every interaction can unfold in multiple histories. The system becomes more complex, not just energetically, but informationally. This is where physics and information theory meet. In modern physics, entropy is not just disorder, it is information. More precisely, it's a measure of how many possible internal states a system could have while still appearing the same from the outside. So when temperature rises, you are not only increasing energy, you are increasing the space of possibilities. But that space cannot grow forever without constraint. There is a deep idea in modern theoretical physics suggesting that any finite region of space can only contain a finite amount of information. This comes from black hole physics and the study of horizons and holographic principle. The key insight is surprising. The maximum entropy inside a region is not proportional to its volume, but to its surface area. That means the storage capacity of reality scales like a boundary, not a bulk. If this is true, then there is an upper limit to how many distinct states can exist inside any region of space. And if there is an upper limit to states, there is an upper limit to entropy. And if entropy is bounded, then temperature cannot increase without bound either. This brings us back to the question of infinite heat. To reach infinite temperature, you would need entropy to behave in an unbounded way to keep increasing the number of accessible states without limit. But if the universe has a finite information capacity per region, then at some point you run out of room for new configurations. You cannot pack in more distinguishable states than the system allows. So instead of continuing upward, the system hits a wall. Not a physical wall, but a combinatorial one. A limit of possibility. This idea becomes even more concrete when you think about black holes again. A black hole is not just an object with gravity, it is also the most information-dense object possible for its size. Its entropy scales with its event horizon area, not its volume, suggesting that it is saturating the maximum possible information content. In this sense, black holes are not just endpoints of collapse, they are the universe's way of enforcing an upper bound on information density. And since temperature is linked to how energy distributes across possible states, this bound indirectly constrains temperature itself.
Now step back and look at the full chain. As energy increases, matter breaks into particles. Particles break into fields. Fields interact with space-time. Space-time forms horizons. Horizons limit information. Information limits entropy. Entropy limits temperature. At each stage, something fundamental restricts the path toward infinity. Not a single law, but a layered structure of constraints. This leads to a powerful interpretation. Infinite heat is not something forbidden by a single rule. It is something prevented by the consistency of the entire framework of reality. To reach it, you would need to break quantum mechanics, relativity, thermodynamics, yes, and information theory simultaneously. And every time physics is pushed toward that edge, it responds by changing the rules of description itself. So what remains at the end of this journey? Not a number, not a state, but a limit of meaning. A point where hotter stops being a useful concept, not because nature is incomplete, but because our language of temperature is built on assumptions that no longer apply. Temperature, as defined in physics, depends on something very specific: the ability to meaningfully distinguish between energy states. You need a system. You need identifiable degrees of freedom. You need a way to count configurations. But at extreme energy densities, something begins to interfere with this process at a fundamental level: quantum uncertainty. At small enough scales, energy cannot be localized precisely. The more tightly you try to confine energy into a region, the more uncertain its behavior becomes. Fluctuations are no longer small corrections. They dominate. This is not just about particles jittering. It's about space-time itself losing stability. At scales approaching the Planck regime, space-time is no longer smooth or continuous. It cannot be treated as a fixed background where events happen.
Instead, it becomes dynamic, fluctuating, uncertain. Distances blur, intervals of time lose precision, causality itself becomes less sharply defined. This is sometimes described as a kind of quantum foam, not a substance, but a way of expressing that geometry itself is no longer well defined. In such a setting, what does it mean to assign a temperature? Temperature assumes equilibrium, a stable system where probabilities can settle into a distribution. But here, there may be no stable notion of state at all. No fixed geometry, no clear boundary, no consistent time evolution. Without these, the statistical foundation of temperature collapses. There is another layer to this breakdown, tied to how energy behaves when pushed to extremes of localization. If you attempt to concentrate energy into an increasingly small region to raise temperature, quantum mechanics resists. The uncertainty principle ensures that high localization leads to large fluctuations in momentum and energy. But gravity adds a second constraint. As that localized energy grows, its gravitational influence increases. beyond a certain point, the region collapses into a horizon before you can define any finer structure inside it. So two limits converge. Quantum uncertainty prevents precise definition of energy states. Gravity prevents access to regions where those states would exist. Between them, the idea of a well-defined microscopic configuration, the very thing temperature depends on, disappears. Now consider what this means for the concept of infinite. To approach infinite temperature, you would need to define arbitrarily high energy states, distinguish them clearly, allow them to be populated in a statistical sense. But in this regime, none of these conditions hold.
This reframes the entire question. Infinite heat is not just unreachable in practice, it may not exist even in principle within a consistent physical theory, because reaching it would require a system that has infinite distinguishable states, allows infinite energy density without collapse, maintains a stable notion of time and equilibrium, and preserves the ability to define probabilities. Every known direction in physics removes at least one of these requirements as you approach extreme limits.
At ordinary scales, a physical system evolves in time by changing its state. Particles move, fields oscillate, energy redistributes. Temperature describes how these changes are statistically organized. But there is a deeper question hiding underneath. How fast can a system change? Not how much energy it has, but how quickly it can move from one distinguishable configuration to another. Because if temperature is tied to energy, and energy drives change, then pushing temperature toward extremes is also pushing the rate of physical evolution toward a limit. Quantum mechanics imposes a bound on this. A system with energy E cannot evolve arbitrarily fast between distinguishable states. There is a fundamental limit relating energy to the minimum time required for a system to become measurably different. This is captured in results like the Margolis-Levitin bound, which ties energy directly to the maximum rate of computation, or more generally, the maximum rate of state change. In simple terms, more energy allows faster evolution, but not infinitely fast. There was a ceiling. Now connect this to temperature. At higher temperatures, systems explore their possible states more rapidly. Collisions happen more frequently. Transitions between configurations accelerate. So increasing temperature is not just about accessing higher energies, it is about increasing the rate at which the system processes its own possibilities. In that sense, a hot system is one that is computing its configurations very quickly. But if there is a maximum rate at which any physical system can evolve, then there is also a maximum meaningful rate at which it can explore its state space. You cannot have transitions happening faster than this bound. Which means that even if you keep adding energy, there comes a point where the system cannot translate that energy into faster distinguishable change. The connection between energy and evolution begins to saturate. Now bring gravity back into the picture. If you try to increase energy density further to push this rate higher, gravitational effects intervene again. Horizons form, limiting the ability of information to propagate outward. From the outside, the system appears to slow down, not speed up. Time dilation becomes extreme. Clocks near high-energy regions tick more slowly relative to distant observers. So while locally the system might be extremely energetic, globally its ability to evolve in an observable way becomes suppressed. This creates a deep tension.
Quantum mechanics sets a maximum rate of change. Relativity distorts time under extreme energy during extreme energy. Information theory limits how many states can exist. All three converge to restrict how fast reality can unfold. And since temperature is tied to how energy drives transitions between states, these limits indirectly cap what temperature can mean. Now, consider the following. To reach infinite temperature, you would need infinite energy per degree of freedom, infinite rate of transitions between states, infinite distinguishability of configurations. But quantum bounds prevent infinite transition rates. Gravitational effects prevent arbitrary energy localization. Information limits prevent infinite distinguishability.
So the path toward infinity is blocked not at one point, but along every axis that defines temperature. There is another way to see this. Imagine trying to measure temperature in such an extreme system. You would need a thermometer, some device that interacts with the system and equilibrates with it. But equilibration itself takes time. And if the system evolves at or near the maximum allowed rate, no slower measuring device can keep up. The act of measurement lags behind the system's evolution. At some point, the idea of assigning a stable temperature becomes impossible, not because the system is too hot, but because it changes too rapidly to be characterized. So temperature, which began as a simple measure of hotness, now reveals itself as something far more constrained. It depends on the existence of stable states, the ability to transition between them, the rate at which those transitions occur, and the capacity to measure and compare those states. Push all of these to their limits, and the concept does not diverge. It dissolves.
Quantum mechanics sets a maximum rate of change. Relativity distorts time under extreme energy during extreme energy. Information theory limits how many states can exist. All three converge to restrict how fast reality can unfold. And since temperature is tied to how energy drives transitions between states, these limits indirectly cap what temperature can mean. Now, consider the following. To reach infinite temperature, you would need infinite energy per degree of freedom, infinite rate of transitions between states, infinite distinguishability of configurations. But quantum bounds prevent infinite transition rates. Gravitational effects prevent arbitrary energy localization. Information limits prevent infinite distinguishability. So the path toward infinity is blocked not at one point, but along every axis that defines temperature. There is another way to see this. Imagine trying to measure temperature in such an extreme system. You would need a thermometer, some device that interacts with the system and equilibrates with it. But equilibration itself takes time. And if the system evolves at or near the maximum allowed rate, no slower measuring device can keep up. The act of measurement lags behind the system's evolution. At some point, the idea of assigning a stable temperature becomes impossible, not because the system is too hot, but because it changes too rapidly to be characterized. So temperature, which began as a simple measure of hotness, now reveals itself as something far more constrained. It depends on the existence of stable states, the ability to transition between them, the rate at which those transitions occur, and the capacity to measure and compare those states. Push all of these to their limits, and the concept does not diverge. It dissolves.
Up to now, temperature has been treated as something local, defined within a box, a plasma, a collapsing region. But the universe is not sitting inside anything larger. It is the full system. So if there is any ultimate limit to heat, it must also apply cosmologically. And here, something unexpected appears. The universe does not allow arbitrary energy density everywhere at once. In cosmology, energy density is tied directly to expansion. Pack more energy into the universe, and its geometry responds, not by staying static, but by evolving. At extremely high energy densities, like those near the earliest moments after the Big Bang, expansion is violent and rapid. Space itself stretches, carrying energy with it, diluting it over time. This creates a natural regulator. If energy density becomes too high, the universe does not sit there and heat indefinitely. It reacts. It expands.
This expansion does something crucial to temperature. As space grows, wavelengths stretch, energies decrease. What was once extremely hot begins to cool, not because energy is lost, but because it is spread out across a larger structure. So even if conditions approach extreme temperatures, the dynamics of spacetime itself push the system away from that regime. Heat disperses through geometry. Now consider the opposite possibility.
Instead of spreading out, what if energy is forced into a confined region on cosmic scales? Gravity takes over again. Regions with sufficiently high energy density collapse, forming black holes or other compact structures. These do not allow unrestricted growth of temperature either. They isolate energy behind horizons, limiting interaction with the rest of the universe. So whether energy tries to spread or concentrate, there are mechanisms that prevent it from sustaining an unbounded rise in temperature. There is also a more subtle constraint tied to the total information content of the universe. If the holographic arguments hold not just locally but globally, then the observable universe has a finite maximum entropy, a limit on the total number of distinguishable configurations it can contain. That means the universe cannot explore an infinite number of states. And if temperature is tied to how energy distributes across states, then the total thermal capacity of the universe is finite as well. Not small, but not infinite. Now connect this back to evolution. If the universe had regions of truly infinite temperature, they would correspond to regions with unbounded energy density, unbounded entropy, unbounded rates of state change.
But such regions would violate every constraint we followed. They would collapse gravitationally, they would exceed information limits, they would disrupt causal structure, they would eliminate any stable notion of time. In other words, they would not behave like parts of a universe. They would erase the conditions required for the universe to be describable at all. There is one more layer. In an expanding universe, there is a horizon, not just around black holes, but a cosmological horizon. There are regions of space that can never influence each other because of the rate of expansion. This horizon also carries entropy and temperature. Even empty space, on the largest scales, has a kind of background temperature associated with it. This means temperature is not just a property of matter anymore. It is woven into space-time itself. So when you push the idea of heat to its extreme, it doesn't just affect particles. It touches geometry, causality, information, and the limits of observation. At that point, asking how hot can something get becomes inseparable from asking what can the universe itself allow to exist.
This expansion does something crucial to temperature. As space grows, wavelengths stretch, energies decrease. What was once extremely hot begins to cool, not because energy is lost, but because it is spread out across a larger structure. So even if conditions approach extreme temperatures, the dynamics of space-time itself push the system away from that regime. Heat disperses through geometry. Now consider the opposite possibility. Instead of spreading out, what if energy is forced into a confined region on cosmic scales? Gravity takes over again. Regions with sufficiently high energy density collapse, forming black holes or other compact structures. These do not allow unrestricted growth of temperature either. They isolate energy behind horizons, limiting interaction with the rest of the universe. So whether energy tries to spread or concentrate, there are mechanisms that prevent it from sustaining an unbounded rise in temperature. There is also a more subtle constraint tied to the total information content of the universe. If the holographic arguments hold not just locally but globally, then the observable universe has a finite maximum entropy, a limit on the total number of distinguishable configurations it can contain. That means the universe cannot explore an infinite number of states. And if temperature is tied to how energy distributes across states, then the total thermal capacity of the universe is finite as well. Not small, but not infinite. Now connect this back to evolution. If the universe had regions of truly infinite temperature, they would correspond to regions with unbounded energy density, unbounded entropy, unbounded rates of state change. But such regions would violate every constraint we followed. They would collapse gravitationally, they would exceed information limits, they would disrupt causal structure, they would eliminate any stable notion of time. In other words, they would not behave like parts of a universe.
they would erase the conditions required for the universe to be describable at all. There is one more layer. In an expanding universe, there is a horizon, not just around black holes, but a cosmological horizon. There are regions of space that can never influence each other because of the rate of expansion. This horizon also carries entropy and temperature. Even empty space on the largest scales has a kind of background temperature.
This expansion does something crucial to temperature. As space grows, wavelengths stretch, energies decrease. What was once extremely hot begins to cool, not because energy is lost, but because it is spread out across a larger structure. So even if conditions approach extreme temperatures, the dynamics of spacetime itself push the system away from that regime. Heat disperses through geometry. Now consider the opposite possibility. Instead of spreading out, what if energy is forced into a confined region on cosmic scales? Gravity takes over again. Regions with sufficiently high energy density collapse, forming black holes or other compact structures. These do not allow unrestricted growth of temperature either. They isolate energy behind horizons, limiting interaction with the rest of the universe. So whether energy tries to spread or concentrate, there are mechanisms that prevent it from sustaining an unbounded rise in temperature. There is also a more subtle constraint tied to the total information content of the universe. If the holographic arguments hold not just locally but globally, then the observable universe has a finite maximum entropy, a limit on the total number of distinguishable configurations it can contain. That means the universe cannot explore an infinite number of states. And if temperature is tied to how energy distributes across states, then the total thermal capacity of the universe is finite as well. Not small, but not infinite. Now connect this back to evolution. If the universe had regions of truly infinite temperature, they would correspond to regions with unbounded energy density, unbounded entropy, unbounded rates of state change. But such regions would violate every constraint we followed. They would collapse gravitationally, they would exceed information limits, they would disrupt causal structure, they would eliminate any stable notion of time. In other words, they would not behave like parts of a universe. They would erase the conditions required for the universe to be describable at all. There is one more layer. In an expanding universe, there is a horizon, not just around black holes, but a cosmological horizon. There are regions of space that can never influence each other because of the rate of expansion. This horizon also carries entropy and temperature. Even empty space on the largest scales